All right, welcome back. This time we're going to be talking about normality and quotients, and we'll see what exactly that entails. First, I want to say there are several questions at this point which we might already be wondering or which naturally arise out of cosets. Question 1. Last time we introduced the idea of congruence mod H, which we said was a relation, and then we went further to say it's a congruence relation on a group G if H is a subgroup of the group G. So now we can ask, left and right congruence, is there ever a time when they coincide? And what do we really mean by coincide here? Is there ever a time when it partitions the group as an equivalence relation into the same equivalence classes? Question 2 that we might ask, when is every left coset of, say, H and G also a right coset of H and G for obviously different elements? We're not saying that AH has to equal HA for some element A in the group G. This is a special case of that, but we're saying when is this set, this coset also a coset on the other side by maybe two different elements. As a special case, of course, they could be the same element, but not in general. The third question we might ask is based on the clarification of the second. When does this statement hold AH equals HA for all A in the group G? And the last question I want to ask is, when is our new relation congruence mod H, hinted at by the name of course, a congruence relation? What is a congruence relation? Just a quick review. It is an equivalence relation that respects the binary operation in the group. So for instance, if we have group elements A, B, C, and D, and A is congruent to C, and B is congruent to D, then this would imply, if it's a congruence relation, that A times B is congruent to C times D, right? We let the binary operation of the group into this mix and it does not change anything. Exactly what we would expect to happen in a congruence situation is what happens. Now what's interesting here is that all of these questions, as well as several others that I didn't mention, lead to the idea of what's called a normal subgroup. We will define that, we will give examples, we're going to prove theorems, and then we're going to talk about why normal subgroups are important. Now before I even define a normal subgroup for you, I'd like to give a quick overview of why they matter. There's basically three reasons I've come up with, although they're not necessarily mutually disjoint reasons. They play into each other largely. The first reason is classification. We're going to see that normal subgroups help us detect whether a group is isomorphic to a direct product group. So is it really built out of simpler groups? The second reason is that they allow us to form something called quotient groups, which is a very useful and essential idea in group theory. And the last reason, which I'm going to save for the next video, is that normal subgroups play very nicely with homomorphisms. And we'll see what that means exactly. I'm going to save that for the next video because I want to do lots of examples. I want this to be an example-heavy video because I think quotients and normal subgroups are not really easy to understand at first as far as motivating them. So I want you to have lots of examples to think of before we move on to the really important theorems. Alright, so I'm going to start with what we talked about last time and just arbitrarily choose right congruence instead of left congruence, but it's the same. So we're going to assume now that it's not only an equivalence relation, which we proved before, but that it's a congruence relation. So just to review, if H is a subgroup of G and A and B are elements of the group G, not necessarily in H, A right congruent to B means that A times B inverse is in the subgroup H, right? We showed this was an equivalence relation. Now we're going to add the further property that A congruent to C and B congruent to D. I'm just going to write congruent instead of right congruent. Please take my meaning accordingly. And these two together now imply that A times B is congruent to C times D. All right, so how's this going to help us? Well, let's first look at A congruent to C, and let's set C equal to A. We know this is true because of the reflexive property of equivalence relations. So A congruent to A is true. And then I want to take an arbitrary element H from the subgroup capital H. So we'll say let H be in big H. And is H inverse, I'm going to ask, right congruent to the identity element? I'm going to say yes, because the inverse of the identity element is the identity element. So that H inverse times E inverse, which is just E, is going to be H inverse, and that's obviously an H because H is a subgroup, so it contains its own inverses. So H inverse is indeed right congruent to the identity element. Now, these two facts together, plus this property of congruence relations, gives us that A must be right congruent to AH inverse, right? Now, by definition, this means that A times AH inverse is in the subgroup capital H. Now, if we use our law for inverses, this means that AH times A inverse is in the subgroup H. And since this is true for all arbitrary elements H of this subgroup, that means, and for an arbitrary element A of G as well, that means that big H, A inverse, is equal to H, right? It sends all of the elements of H to H. And this is exactly the property which we say defines a normal subgroup. So, by definition, H is normal in G. This is what we say. A normal subgroup is normal in the group. H is normal in G, denoted with this little triangle. So H is normal in G whenever this statement is true. And we usually use a capital N for a normal subgroup, although it doesn't really matter. And all we did to get there was looked at the equivalence relation defining cosets, which we analyzed last time, and giving it this further property that it's a congruence relation. This leads naturally to the idea of the normal subgroup. We're going to see that normal subgroups are very important, although we're going to go through some examples first to solidify what exactly they are. All right, first example is the trivial group. It is always normal in the group. How do we know? Well, we take an arbitrary element little g from the group, and we take this times every element in this group, which is just E, times G inverse. And what does that give us? Well, this is the identity, so it's going to be just G inverse times G, and that's going to cancel to give us the identity again. Since this is true element-wise for every element in this set, which is just a singleton, then we have a normal subgroup. All right, second example. How about Zm in Zm times n, where m and n are positive integers? All right, how do we show this? Well, an arbitrary element from this is just some positive integer between 0 and m minus 1. So we'll just say it's k in Zm. And we'll pick some second one in this. It goes all the way up to mn minus 1. We'll call it L. Our question is it true for arbitrary k and L that LK, L inverse, is in this group, or Zm. And additively, because this is a commutative group, we can write this as is L plus K minus L in Zm for all L and K? And the answer is yes, and trivially so, because in a commutative group, we can actually switch these terms, and then we have L minus L, and that's just the identity. So we already see that for abelian groups, this is always true. All right, for our third example, we're going to look at the matrix representations again of the special linear and general linear group over the real numbers. So if we have an arbitrary element of SL, we'll just call it S so we don't get confused, and an arbitrary element of GL, which we'll call G. The question is going to be, is the product GS G inverse always going to be in the special linear group. And you'll recall the special linear group is those subset of those matrices in GL which have exactly determinant positive 1. All right, so if S has this property, then the determinant of S is of course positive 1. So what's the determinant of the product is ultimately what's going to determine if it's in the special linear group. So the determinant of GS G inverse by the properties of matrices and determinants, or not, determinants, is going to be the product of G times the determinant of S times 1 over the determinant of G, which is the determinant of G inverse, of course. And these are just real numbers, which we're multiplying in the normal sense, so that we can flip these and those two cancel out. And the determinant of S, we said because it's in the special linear group, is exactly 1. So the whole thing has determinant 1, which means it is in the special linear group. Since this is true for all matrices G and S, we conclude that the special linear group of a given dimension, of course, is normal in the general linear group of that same dimension. Now I'd just like to make a quick note that H is normal in G if and only if G, H, G inverse is equal to H for all G in the group G. Of course, we said that as our definition of normal subgroup. I'd like to point out that G, H, G inverse, this right here is what you'd call conjugation by the element G. So conjugation of the group H, or subgroup H, by the element G. So conjugation of H by G. Remember this terminology. All right, so the second example leads us to our first theorem. If G is an abelian group, then every subgroup of that abelian group is going to be normal in it. And I would like to point out at this point that normal subgroups, when you talk about a subgroup being normal, it's not inherently normal. We talk about it being normal in the larger group. If you compare it to a different group, say you have 3 groups which are cascadingly contained in one another. So you have H inside of G inside of, say, B. Well, it does not mean that H is normal in B because H is normal in G. Keep that in mind. Now, why is this true? Well, it's really simple, right? G inverse, right, is the set of all elements G, little h, G inverse, where H is in the subgroup H. But of course, because G is an abelian group, we can write this as HG, G inverse, and then these cancel out, and you get the identity element multiplied by H is just H, so the set of all H such that H is in subgroup H, and this is just the subgroup H, right? QED. All right, next theorem. So if n sub I, we're transitioning to use n as normal subgroup now. If that's an indexed family of normal subgroups, so a collection of them in the group G, then the intersection of all those normal subgroups is also a normal subgroup in G. Well, the proof here is pretty simple as well. So let eta be an element in the intersection of these normal subgroups, and let G be an arbitrary element of the group capital G. Then what we want to find out is if the product G eta G inverse is in this intersection for all G and eta, of course. And how do we know that it is? Well, let's pick an arbitrary element here, or arbitrary set in this intersection rather. We know that G times eta times G inverse is going to be, by definition, in an arbitrary, let's just call it NJ, normal subgroup. Why is this true? Because eta must be in n sub j in order to be in the intersection, and we know that that this is normal in G, right? That's one of our suppositions here. So that this product has to also be in this subgroup. Now, if this is true for every nj, then that means it's also in the intersection. right? For all j implies, in the indexing set I, implies that G eta inverse, or G eta G inverse rather, is in the intersection of all the ni's as well. And thus, by the definition of normal subgroup, this intersection is also normal in G. All right, next theorem. If H is just a usual subgroup in G, and the index of H in G is 2, right? There are 2 cosets you can form of H in G, then H is also, as a product of that, normal in the group G. All right, so how do we prove this? First, let's suppose that we have an arbitrary element in the subgroup H. If that's the case, then G little h G inverse for any little h in the subgroup big H is going to be equal to a member of H times a member of H times a member of H, since it's a subgroup, and being such, it's closed. So this is obviously going to be in the subgroup H. And in that case, we're done. Now suppose that G is specifically not in the subgroup H. Well, then what we want to show next is that GH is not equal to H, where this is the left coset of H in big G by little g. Now to see this, all we have to do is take an arbitrary element H1, and if it were true, then this would be equal to H2, where H1 and H2 are in H. Well, since G is a group, we can multiply on the right by H1 inverse and get G is equal to H2 H1 inverse. Now since H2 and H1 are both in the subgroup H, and it is closed, then G on the other side of the equal sign must also be in H. But we assumed it's not, so this can't happen. So this means that the left coset of H in the group by this element, G, is not equal to H. The same can be said of the right coset of H in G by little g. It is not going to be equal to the subgroup H. Now, since the index of H in G is only 2, there are only 2 cosets, and one of them is H, which means both of these, not being H, must be the other one, and thus they must be equal. So that GH is equal to HG, and this is our defining property, or one way of writing our defining property, for a normal subgroup H, right? This is true for arbitrary elements G. Now I want to talk about why normal subgroups matter. And I said classification of groups was one of those reasons. Now normal subgroups are so important that they figure into this in a lot of different ways. But just to start, one way is that they allow us to filter out some groups as candidates for direct product groups. In other words, if we're just looking at some group and asking the question, is this isomorphic to a direct product, i.e., is it built out of smaller groups or not? The first thing we might do is look for normal subgroups. All right, so we're going to let the pair G1 and the identity of H be in this group, just an arbitrary element, and likewise G2H be an arbitrary element of this direct product group, where G1, G2 are elements of the group G, and H is obviously an element of the group H. Now what we're going to do here is just very simple. We're going to use the definition of normal subgroup again. These are all arbitrary elements, and we're going to take this element, G2H, times this element, G1, identity in H, times this element again, inverse, right? So G2H inverse. And we proved a lot of theorems about direct products in an early video, so you might want to go back and review that. But we've shown before that the inverse of this direct product element is going to consist of the individual inverses. All right, and then we're just going to have element-wise, coordinate-wise if you like, multiplication. So this is going to be equal to G2, G1, G2 inverse, comma, H, E sub H, H inverse. Now, by definition, every element commutes with the identity element, and in fact it's just going to be equal to that element, so that then these two multiplied together are going to equal the identity again. And this G2 times G1 times G2 inverse by closure is another element in the group G. So this is going to be equal to something in G, we'll just call it X, comma, the identity in the group H, right, where X is in G. And by definition, this is in the direct product of G times group generated by the identity element, or the trivial subgroup of the group H. So it is true that this group is normal inside of that group. Now, this property is so important that it merits a definition. A group G is said to be simple, it's a simple group, if there exists no non-trivial proper subgroups which are normal in that group. In other words, if we exclude the identity group and we exclude the group itself, so non-trivial proper subgroups, if you can find no other subgroups than these two of a group G that are normal in G, then G is said to be a simple group. The discovery and classification of all finite simple groups is actually complete now, and is widely considered to be one of the greatest mathematical achievements of the community ever, spanning I think it's like 100 years and just a ton of mathematicians' work. But it's done, and you can actually look up the tables, you can look up the classification to see the categories of all finite simple groups. It's very interesting. All right, so the second reason I want to talk about as far as why normal subgroups matter is quotients. This is sort of what the discussion of cosets and equivalence relations, this is the natural end to which that discussion leads. I'm going to introduce you now to an idea which is not immediately intuitive. But suppose we want to multiply two cosets together. Now, I don't mean multiplication in, the traditional number sense, and I don't mean multiplication in the sense of the group operation in G. I mean a third and totally new type of multiplication, but closer to the second, right? So suppose we have two cosets, two left cosets. I'm just going to arbitrarily choose left cosets here. Same is true for right. Suppose we want to take the product of two cosets. Well, how would we define this? Is there a natural way to define this? Well, I would argue yes, there is a natural way. Take the coset of H and G by the product A times B, right? This is a natural way to define multiplication of cosets if you wanted to do such a thing. And of course, the next question you'd want to ask is this product well defined? Well, the answer is conditionally yes. So our next theorem is that multiplication of cosets in the way I just showed you is well defined if and only if our subgroup that we're taking cosets of is normal in the group. So only if H is a normal subgroup of the group G. So first let's go this way and suppose H is a normal subgroup of G. Then if we have elements A and B, which are just arbitrary in the group G, and let's select H1, H2, and H3 to be arbitrary elements of the subgroup H. So we want AH times BH to equal AB times H, right? We want this statement to be, we want this to make sense, and we want it to be true. All right, well, in order to do that, let's multiply out element-wise, right? So what we're essentially saying is that we want an arbitrary product from an arbitrary A and G and an arbitrary H1 in the group H times, same story here, B times another element, H2, to be equal to A times B times a third element from H. And these could overlap, but in general they are not the same H values. So now if we just do a little bit of manipulation, we can cancel on the left because we're in the group G. And after we cancel, what we can do is multiply through by H2 inverse on the right, so that we have H1 times B is equal to B H3 H2 inverse. What I'd like to point out at this stage is that these are just arbitrary elements of H. If I simplify things a little bit, we can just call this product H star, and then we have H1B is equal to B H star. And what we're saying is that given an element in the group G, calling it B, arbitrary, and an arbitrary element of H called H1, there must exist this element in the subgroup H such that, calling it H star, such that H1B is equal to BH star. Now this is the definition of a normal subgroup, it's just element-wise, right? This is to say that H1 times B, and then times B inverse on the left must equal H star. In other words, the product for all arbitrary, let's just say arbitrary H, arbitrary B, B inverse HB, or this is the same essentially as saying BHB inverse when everything is figured out, must be in the group H, right? This is exactly what we mean by normal subgroup. So multiplication of cosets being well defined implies that we have a normal subgroup on our hands. Now in order to show it the other way, I'd like to show you how illuminating the congruence relation view of normal subgroups is. This is one of its shining moments. So we already know that the notions of H normal in G and the congruence relation defined by congruence mod H on elements in the group G, when that is a congruence relation, those two notions coincide. Now we know for all elements A, B, X, and Y in the group G that A left congruent to X and B left congruent to Y together imply that AB is left congruent to XY. Now starting from the other definition, X is in the left coset of H and G by A if and only if X is equal to A times little h for some element of the subgroup H, which means that A inverse X is equal to H, which means A inverse X is in the subgroup H, which is, once again, if and only if A is left congruent to X mod H, by definition of congruence mod H, right? The same could be said for Y. Since we know this is true, we can follow this chain of if and only ifs back to show that X is in the left coset AH, and Y is thus also in BH. Now, what we want to show is that this implies that XY is in the product AB H. All right, again, since we have these two statements, which are equivalent to these two statements, they imply in a normal subgroup that this is true, right? Mod H. So what we have is the following, that if X is in the left coset AH and Y is in the left coset BH, we're going to have this statement, which we can translate in the same way we translated this to this, only backwards. We're going to have that AB inverse times XY is going to be in H, which means that it is equal to some little h, not necessarily the same one here, just so we're clear. And then we can multiply through and we can say this means that XY is equal to AB times H, and this is exactly what we mean by it being contained in the left coset, right? So we have XY is contained in AB H, right? And something that might not be clear to you at this point, but is really what's going on behind the scenes here, the reason we need this to be true is that when we multiply cosets, we don't want it to be dependent on which elements we're choosing. What I mean by that is this. If we have AH and BH and we're multiplying them together to get little a b times h, what we don't want is to change this element A to another element that gives you the same coset, but then this coset changes, right? Our multiplication is not going to be well defined in that manner. So in order for it to be well defined, we need this. We need that any elements which are congruent to, so in order for it to be well defined, we need that any element in this coset and any element in this coset have the property that when you multiply them, you get an element in this coset. And that's what we have just shown by assuming that H is normal in G. So multiplication of cosets is well defined. It makes sense as a binary operation. Now, binary operation lingo should be pretty familiar by now. We can start talking about, perhaps, we can form a group or some algebraic structure using this new multiplication operation of cosets, right? Not element-wise, but now our new elements are going to be the cosets themselves, given some fixed subgroup. All right, so all of this has led us to this theorem. If n is a normal subgroup of G, then this, which we're defining to mean the set of all cosets of n and G, forms a group under the multiplication of cosets we just defined, and that group has order index of n in G. So by only using normal subgroups, as we saw in the last theorem, we don't have to worry about the operation of multiplication of cosets being well defined. You're not going to multiply two cosets and get something that isn't a coset. So we know that it's closed. All right, the second thing we might want to check is for an identity element. Well, suppose we take just the identity of the group G and multiply it by the subgroup N, right? So if we have En times, say, An for some arbitrary A and G, then since N is normal, we get this, and this results in that, right? So it's, and you can do it the same in the other order, so that this, which is just the subgroup N, right? This coset is just the identity coset, if you like. Or equivalently, it is exactly that congruence class under congruence mod N, which contains the identity element. That's an important view here. This is going to be our identity element in this new group, which consists of the set of all left cosets under multiplication of cosets. Equivalently, you could use right cosets, but just by convention, let's use left cosets here. So we have an identity. The next question you might ask, is it associative? Well, if we have An times Bn, this is equal to Abn times Cn, and then again by our definition, this is AB times C, parentheses, times N, and then because A, B, and C are all elements of the group G, it's associative. So A times B times C times N, and then you work your way back up, right? So we have An times BC times N is equal to An times Bn times Cn, right? So we do have associativity, and it follows from associativity under the normal group law. And inverses are not going to be a problem. If you take an arbitrary element A and G and multiply it by A inverse N, right? This is equal to A inverse N is equal to En is equal to N, which we said was our identity element. So we are going to have inverses, and it follows from the group having element-wise inverses. So if we have a normal subgroup, then the set of all left cosets, or respectively the set of all left or right cosets, form a group under multiplication of cosets, as we can see, because it satisfies all the group axioms. Now what's interesting about this is that the normal subgroup requirement was only really required to make multiplication of cosets make sense to begin with, right? To make sure it was well defined. All these other properties really just follow from the group being a group. As far as this statement goes, well, the definition of the index of n and g is the number of left cosets, or respectively right cosets of n and g. So by definition, the set of all left cosets has to have cardinality equal to that. That's how we define it. So this group we've just formed under multiplication of cosets is an extremely important one, which we're going to devote a lot of time to. And I'm just going to do a ton of examples after this so you can really internalize what this thing is. And it is called a quotient group. We call it the quotient of G by N, right? Also, we call it a factor group sometimes, but the most common I would say is the quotient group of G by N. Super important. All right, the rest of this video is just going to be dedicated to giving you examples of quotient groups so that you can help internalize this concept. All right, first example is going to be Z quotient MZ, where M is some positive integer. So if this were 2, then MZ would be all the even integers. If it were 3, it would be all the multiples of 3, etc., etc. So what's the actual group going to consist of here? Well, it's going to be cosets of MZ in Z, right? So it's going to have an integer multiplying the entire subgroup, which is all the multiples of that. But of course, this is actually an additive group, at least the way we normally talk about it. So it's actually going to be N plus MZ, if you like. So we're going to pick one integer and add all the multiples of M to that integer. Now watch what happens. We're going to say do 0 plus mz, which is just going to be equal to mz. Then we're going to have 1 plus mz, right? It's going to be 1 more than all the multiples of m. Then we're going to have 2 plus mz. This is going to be all numbers in the integers which are exactly 2 more than all the multiples of m. 3 plus mz, etc., until we get to m plus 1, or m minus 1, sorry. m minus 1 plus mz, right? And this is going to keep happening. But then once we hit m plus mz, what's going to happen? Well, adding m to every multiple of m in the integers is just going to give you another multiple of m in the integers, which means this coset is unchanged by adding a multiple of m. Right? And so m plus 1, it's going to be adding m, which does nothing, and then plus 1. So what you're going to get is that this cycles back to this, and the next one cycles back to this one, so that these m cosets, 0 plus mz, 1 plus mz, all the way to m minus 1 plus mz, are going to be your m different cosets of mz and z. And notice the cyclical nature of this. And I say cyclical on purpose here because it's a cyclic group and it's one we are familiar with. This is isomorphic to none other than z sub m under modular addition, right? Where we add our integers mod m, right? Integers modulo m. We've seen this 1,000 times. Well, it is none other than this quotient group of the integers by multiples of some positive integer. All right, next example is going to be the multiplicative complex numbers, without 0 of course, quotiented by the multiplicative real numbers without 0, which we've seen a couple times as examples of groups. Well, I believe we showed before that if we have the complex plane, we're picking some number a plus bi, right? And then we're taking this element and taking the coset of that, right? What we do is scale it, essentially, so that we get a line in the complex plane excluding the origin. This is the coset of the multiplicative real numbers by this number a plus bi in the complex plane, right? And we have a different coset going through the origin, except not actually going through the origin, but almost going through the origin with that 1 point excluded, for every different complex number, right? These constitute the cosets. So we're actually multiplying these lines together to get our quotient group, right? Each line is an element of the quotient group. All right, next example is going to be the quotient of the orthogonal group by the special orthogonal group. The latter is normal and the former. So what we're going to see is that an arbitrary element of this, we'll call it O, times an arbitrary element of that, we'll call it S. Let's look at the determinant of that. Well, determinant of a product is equal to the product of the determinants, and because this is in the special orthogonal group, which is a subgroup of the special linear group, this is going to have determinant 1, so this is just going to be equal to the determinant of O. Now, O only has two possibilities, right? And this is, the determinant is what distinguishes these two groups, essentially, at least in their matrix representations. And so the determinant of O could only be one of two choices, right? It could be positive 1 or it could be negative 1. So every matrix in the orthogonal group is going to generate a coset of the special orthogonal group, which is those matrices which all have positive 1 as their determinant, or those matrices which have determinant negative 1. So there are two cosets, right? There are two cosets of SO and O, and this means that O quotient SO is going to be isomorphic to the only group which has two elements, Z2, right? So next example, the plane considered as additive vectors, if you like, or just coordinate pairs, but only considered under addition, quotiented by the lattice Z2, right, which is going to consist of all the integral points on the plane, right? So if we have a little grid here, at 1, 0, 1, at 1, 0, at 1, 1, we're all going to have integral points, and these are going to go on in every direction. And this is the lattice Z2. It consists of all these points which are exactly at the corners of these 1 by 1 unit squares. And R2, of course, is going to be the entire plane. We're both considering them as groups under addition. All right, so if we choose this element X somewhere in the plane, then a coset of Z2 by X in R2 is going to look like X plus the entire lattice, right? So this means translated, you can look at it coordinate-wise, right? So if we have X1, X2 is our point X, then what we're looking at is X1 plus M and X2 plus N, where M and N are integers, and they're arbitrary integers, right? So every possible coordinate that looks like X1 plus M, X2 plus N, where M and N are integers, counts, right? It's part of the coset. And what that ends up looking like is its own integer lattice, but sort of shifted off from the normal integer lattice, right? Right? So you can look at all these, I'll connect them so you can sort of see. My drawing's not that great. So you're going to form a little lattice, and basically if you were to look at where you are in whichever square you sort of sit in, then you're going to be exactly at that position in every square, and the coset of Z2 by this element is going to consist of this entirely new lattice you formed, all connected to this point. So what ends up happening is the following. You have one of these cosets for every point in any particular square you want to choose. It doesn't really matter which, right? But then if we move, like Pac-Man here, all the way to one side, what's going to happen if we pick a point on the edge, it's going to be equivalent to a point over here, right? These are going to be connected because they're 1 unit apart. So that you cycle back in that direction. Likewise, if you go to the top, you will find yourself at the bottom again, because this point is equivalent to this point, right? They are both part of the same coset. So what this essentially means is that we have just discovered R2 mod 1, 1. So that's what this is isomorphic to. It is the set of all real numbers in the plane, or just the plane, mod 1, 1, right? So we loop back just as we looped back in the integers mod m, say. We can do this with this trick with real numbers as well. There's nothing stopping us from doing this, right? And this quotient group is exactly this group. All right, so now I'd like to introduce to you a new group called the Quaternion group, and it consists of +1, -1, positive I, negative I, etc. with j and k under the following multiplicative rules. So I squared is equal to -1, just like with complex numbers. J squared is also equal to -1, k squared is also equal to -1, and then I times j times k is equal to -1. These make up the multiplicative rules in this, and so basically these are the multiplicative rules for the quaternions, which are something we might talk more about in the future. But for now, just know that they are defined in this way, and you can scale them by real numbers too, and there's nothing wrong with that. But we just want to consider this 8-element group for a second, called the Quaternion group, sometimes denoted by an H, sometimes denoted in other ways. And then we want to take the quotient of this group. I'll spell quaternion out for you. Quaternion group. And we want to take the quotient of H by this group ±1, which is isomorphic to Z2. Now, what are all the cosets here? Well, if we take 1 times ±1, that's going to give us ±1 as a coset. Same thing for -1, so we can just consider both signs at the same time, and that really is the effect of this. Similarly, ±I times ±1 gives us ±I, and etc. And the real question is, what are the multiplication rules under this new quotient group we formed? ±1 times itself is going to be itself, so okay, this is obviously our identity element. ±1 times any of these is obviously the latter. Now, what happens with ±I and ±j? Or let's actually start even simpler, ±I squared. Well, I times itself would be -1. And the only things you can get here are -1 and +1, right? We're multiplying I or -I times itself or each other. So what that's going to give you is ±1. Similarly, because of this rule, we get that ±j squared, considered as a coset, recall, we're going to get ±1 again. Same thing with ±k squared is going to be equal to ±1. So each one of these 4 elements is idempotent, which is interesting. So that is just enough information to tell us which group with exactly 4 elements this is. Recall that there are only 2 groups with exactly 4 elements, and we talked about them when we discussed Cayley tables, right? There is Z4, the cyclic group Z4, and there's Z2 cross Z2, which is usually known as K4 or the Klein 4 group. So in Z4, 1 + 1 is 2, 2 + 2 is 0, and 3 + 3 is 2. So 2 of those elements do not add to themselves to form the identity element. So we can safely say that this is indeed the Klein 4 group, that H, the Quaternion group, quotiented by ±1, which is isomorphic to Z2. This quotient group is isomorphic to K4, the Klein 4 group. All right, so the discussion of cosets has naturally led us to normal subgroups and quotient groups, and will also lead us to the isomorphism theorems eventually. So tune in next time for Normality and Quotients Part 2. Until then, have a nice day.